All right, so with the last one, we were looking at measurements. We were looking at uncertainty in those measurements. So we talked about, we just go back for a second. So with the graduated cylinders, for instance, um, this one goes up by ones. So we can estimate to the 10th place happens to be right on that line. So we would say 24.0 for the bottom of that meniscus. And then similarly for this one, but it goes up by tenths. So we can go to the 100th place in this case. And balances, and I should say, and that's the uncertainty because we're not totally sure about what that final digit's going to be. We know 2.6, whatever it's going to be, looks like approximately 5, could be 2.647. We don't know for certain, but we know those first two. And then balances are similar where we know, or the balance, I guess I should say, knows what those first few digits are going to be, but the last one is sort of just an estimate as well. So even though it's an electronic readout, there's still uncertainty in those measurements. And when we look at chemistry, when we think about science in general, it's going to be important that we keep those that we manage that uncertainty throughout any of the calculations we do. And with that, we're going to be focusing on significant figures. So that's going to help us identify which of the digits in a value are important. And that's going to be kind of the first step. But then the number of significant figures in those values are going to help us determine how exactly we round our final answer when we do a particular calculation. And then there's going to be a set of rules we'll go over for multiplication and division in terms of how we round our final answer, and then the same thing for addition and subtraction. We'll have two separate rules for those different types of operations. But like I said, first we need to be able to identify how many significant figures are in a particular value. And when we're looking at a measurement, when we're looking at a value, if it's got any digit 1 through 9, so 1, 2, 3, 4, 5, 6, 7, 8, 9, anytime we see any of those always represent some value. So those are always going to be significant. So we can see that with the first one, this first rule here, all non-zero digits are significant. So 345.22 centimeters. We've got 5 digits there. None of them are 0. So all 5 of those digits have to be significant. But when we look at values that contain zeros, depending on where that zero is located, depending on kind of the context in which it's located in that value, it may or may not be significant. So if we look at the second rule there, zeros between non-zero digits are significant. I think that's kind of makes sense because if we look at 406.05, we got the 4, the 6, and the 5 that are significant. So of these 5 digits, we automatically know 3 of them are. But it would be kind of weird if the zeros in between some of these significant figures essentially didn't matter. So because the zeros are between significant digits, those are considered significant. And then somewhat similarly, if we took that 6 and changed it to a 0, normally I would do this on my tablet, but I'm working at my desktop right now, so the writing might not be the best, or just take me a little bit to actually get it so it's legible. But if we change that 6 to a 0, now we've got 400.05. Just take a moment, think about how many significant digits would be in that case. So we still know the 4 and the 5 are definitely significant, but what do we think about these zeros here? So like with the, I guess I'll do it like this too. I'll just underline as we go so we know all the significant digits. So again, the first one, everything's non-zero, so everything's got to matter. With the second one, 4, 6, and 5 are automatic. And then each of these zeros are between non-zero digits, so they're going to be significant as well. So if we look at 405, or 400.05, excuse me, we still know the 4 and the 5 are going to be significant. And then in terms of these zeros, it might look a little different than what we have here, because in the case of the 2 zeros in the original example for number 2, they're directly between 2 non-zero digits. But in this case, all 3 of these zeros are still bracketed by non-zeros. Just happens that they're not directly on both sides. But since all of these zeros have significant digits on the outside, they all have to be significant as well. So in terms of the second rule here, the non-zero digits don't have to be right next to the 0, but as long as we have a non-zero somewhere on the left and somewhere on the right, everything in between has to be significant. And then with the next rule here, zeros to the left of the first non-zero digit are not significant. There's a couple ways we can think about this, and I'll show you one in a second on the next slide, or one of the few slides from now when we look at scientific notation. But one way you can think about the zeros to the left of the first non-zero, or zeros at the start of a number, is thinking about this zero out in front of the decimal. So sometimes the zeros after the decimal at the start can be a little tricky, because if we just remove those completely, it does, of course, change the number. But there's really no difference between these zeros at the right of the decimal and these zeros, or this zero to the left. So if we came in and then just added one more zero here, doesn't change anything about this number, doesn't change the value. If we think about the balances, it doesn't make it any more precise, doesn't make it any more certain. So zeros at the start of a number are always going to be not significant, whether it's before or after a decimal. If it's at the beginning of the number, the zeros don't matter. And we'll see with scientific notation, we can actually write this value without these two zeros after the decimal. And that's why they're not going to be important. And if we think again, this is a gram. So if we think about actually working in the lab, we put a sample on the balance and we get this readout. So this tells us we have 34 10,000th of a gram. So we've got enough mass to represent the 10,000th place. We've got enough mass to represent the thousandth place, excuse me. But the sample would be so small that we don't have anything in the 100th place. We don't have anything in the 10th place. So there's really no value in these digits. They're important as placeholders because, like I said, if we get rid of them completely, they change that number, but they're not significant because they don't actually represent any value. We don't have enough of this sample to even fill up any digits here in the 10th or the 100th place. And again, with scientific notation, we were going to be able to write this value without those zeros. So anytime we can exclude it in scientific notation without changing the value, or without changing the level of accuracy or how confident we are in that measurement, those zeros are never going to be significant. So just think about start of the number, doesn't matter where those zeros are. If it's at the start, whether it's before or after a decimal, they don't actually represent anything at that point. But with number 4, we're going to see the opposite. If the zeros are at the end of the number to the right of a decimal. And in this case, it's going to be because they help us increase the certainty of that measurement. So if you think about 45.300 versus just 45.3, in the case of the one we have here, I guess I should underline these because we've got two sig figs there. But in the case of this value we have as the example, if we just had 45.3, so the numbers I've underlined here, we don't know what those next two digits are going to be. They might be 0, 0. They could be a 2 and a 7. They could be whatever they're going to be. But unless we actually have those digits, we don't know for certain what they're going to be. So that's why these are going to be important. This tells us for certain if they're at the end that those digits are 0. They do represent us knowing that they're 0 as well. So with the values at the end of a number, when it comes to a 0, just think about those offer increased confidence in that measurement now. Whereas if we just had 45.3, we don't have as much information as if we had 45.300. And then finally, if the number's at the end, but there's no decimal point, we just can't be certain. So they may be significant, they may not be. So something like in the case of 300, we know for certain that 3 is going to be significant. So we've got at least one sig fig, but we don't know about those zeros. If they're both significant, what we could do is just put a decimal there. And that just is a sort of a notation that tells us both of those zeros are significant. And if you think about it, it's actually no. But if we do put the 0 there, it tells us both of these are significant. If for whatever reason the second or the first 0 was significant and the second wasn't, really the only way we could indicate that is with scientific notation. So we'd be able to include the first 0, but not the second. But again, the big thing with sig figs right now is just identifying how many there are, so that we can then use that information to properly round our answers when we're doing different calculations. And with this, like everything, remember there is practice on Canvas. So if you want to go through this practice, just identifying the number of sig figs, and then we'll also see the operations. There's going to be practice for that as well. So let me just clear this. And then one other way you can kind of remember that in terms of how do we treat zeros as significant or not, is what's known as the Atlantic and the Pacific rule. So both of these are dealing with the decimal. So think about it absent and present in terms of whether there's a decimal in that number or not. If the decimal is present, we're thinking about Pacific, and the Pacific Ocean is on the left-hand side of the United States. So what we're going to do in that case is start at the non-zero furthest to the left. So in the case of 1.250 grams, that means we're starting with that 1. And then what we're going to do is just count all the way to the end of that number. And it doesn't matter if there's zeros at the end, we're just going to count from the left all the way to the right till we get to the end. And then every digit on the way is going to be significant. So if we think about if we had 0.050 in that case, then we would have started at the 5. We would only count over 1, so we'd have 2 sig figs there because the zeros at the front wouldn't matter. But since we have 1.250, all 4 of these digits are going to be significant. And then again, another way you can think about it is if we didn't have that 0 there, if we just had a mass of 1.25 grams, in terms of a calculator or something, they would be equivalent. But in terms of science, the 0 here gives us more confidence in that measurement. Whereas if we just had 1.25, this digit here could be a 3, could be a 1, could be a 0, but we wouldn't know that for certain. So this gives us a better understanding of what that value actually is. And then similarly, if the decimal is absent, absent starts with A, Atlantic starts with A, Atlantic Ocean is on the right-hand side of the country. So in that case, we're going to start at the non-zero furthest to the right, and then just count all the way to the left. So in the case of 12,500 grams, the 5 is the furthest non-zero to the right. That's where we'll start, and then we'll just count all the way to the end on the left. So in this case, we've just got those 3 sig figs there. So if you want to take a moment and try to practice with those rules and identify in these 7 examples, how many significant figures would we have there? And again, you can think about Atlantic or Pacific, or you can think about just the 5 rules that we went through initially. But again, anything 1 through 9 is going to be significant, always. A 0 in between 2 non-zeros is always significant. A 0 at the end of a decimal is always significant, but a 0 at the start never is. So see if you can use that information to identify in these different examples how many significant figures are going to be present. But I would recommend just pausing it, because like always, I'm just going to, just kind of start working through them so it's not just sitting here for a few minutes with just nothing happening. But with the first one, if we think about the Atlantic Pacific rule, we've got a decimal present. So present means Pacific. Pacific is on the left. So we'll start with the first non-zero furthest to the left and count all the way to the right. So we've got 1 with the 7, a second one with the 1, a third one with this one, and that we already know because those are always going to be significant. But then we also know, since we're counting all the way to the end, that makes the 0 significant as well. So we'll have 4 sig figs in that first one. And again, just think about it, 711 versus 711.0. We have more information with this 0.0 now. So that's why it's going to be significant. Again, decimal present. So we'll start on the left-hand side with the first non-zero. That happens to be the 2. And then we'll count right. So we're not going to count that 0. So we'll just have 3. And again, we could put a whole bunch of zeros at the start of that number, but it's not going to change the value. It's not going to change how confident we are in that measurement. So that's why the zeros at the start are never going to matter. In the case of letter C, excuse me, we've got 4 non-zeros for sure, but then we've got this 0 in the middle, but it's in between a 9 and a 7. We could really think about it, it's in between the 9 and the 4, it's in between the 9 and the 3. However you want to do it, it's in between 2 non-zero digits. So every single digit in that value is going to be significant. We'll have 5 total. The next one, probably the easiest one on here because it doesn't have any zeros. So it's just the total number of digits. 1, 3, 4, and 2 are always going to be significant. Doesn't matter if the decimal's here, 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 if there's no decimal at all. Non-zeros are always significant. So we'll have 4 sig figs there. Letter E is kind of similar to B. It's just now we've got another 0 after the decimal, but it's still at the start. So it's essentially just a placeholder. Doesn't represent any value. It's not going to be significant. So we'll just have 4 sig figs there again. And this one's actually a little bit of could be a little bit of a tricky one. But it's actually pretty similar to the first one because we've got a decimal, we've got a 0 at the end. So that makes that significant. Of course, the 1 is always significant. And now we've got 2 significant digits. So that's going to make all of these zeros in between them significant as well. So we'll have, we'll have 6 actually. I can't count apparently. So that should not be a B. So let's just undo that. And again, we could think about this in terms of the Atlantic and Pacific rule. We have a decimal present. Pacific's on the left. We'll start all the way to the left with the first non-zero and just count all the way to the end. So we'll have 1, 2, 3, 4, 5, 6. If we didn't have that decimal there, if we just had 10,000, again, the 1's still going to be significant, but we don't have enough information about the other zeros. So we would likely just say 1 sig fig there. And then with the final one, we've got 6 non-zero digits there right at the end, and then a whole bunch of zeros to begin with, but those don't actually represent any value. Like we'll see in a little bit, we can use scientific notation to exclude those from the number without changing the value at all. They don't give us more information. They don't give us more certainty at all. So we're just going to have 6 there. So we should have 4, 3, 5, 4, 4, 6, 6. 4, 3, 5, 4, 4, 6, 6. Okay, good. I can still do this, so that's always good. And let me erase that so it's not clear all drawings. Okay. And then, like I've mentioned, scientific notation. If you're unfamiliar with scientific notation, we'll kind of go through it now. But essentially what it allows us to do is represent extremely large and extremely small numbers. So the 2 examples here aren't actually that big or that small. So we may not necessarily use scientific notation for something like this, but in chemistry, we're dealing with extremely small atoms. And if we think about 2 grams of hydrogen, so hydrogen is going to be 2 atoms combined. If we had 2 grams of hydrogen, we would have 6.02 times 10 to the 23rd molecules. We'll ultimately learn that's going to be known as a mole. That's one of the most important units in chemistry. But if we had to do a calculation with 6.02 times 10 to the 23rd, that would be written out. That would be 602 with 21 zeros afterwards. So if we actually had to plug that into a calculator, it would take forever, and it would also be really difficult because you may not even be able to see all those zeros at one time. So you may not actually know how many plugged in. And then similarly with extremely small numbers, kind of the same case. So we use scientific notation to just represent those. And we've got a couple pieces to it, as we can see here. The first one being the coefficient. And let's just see if I put more information on the next slide. I can't remember. Yeah. The first part being the coefficient, that's essentially just going to be the number. We'll see that's going to be just any number between 1 and 10, basically, or 1 and 9.9 repeating. Then we've got the base, which is just going to be 10. And that's going to make this somewhat, or relatively easy at least, because essentially what we're going to be doing is just moving the decimal left or right, depending on if it's a big or a small number. And then the second piece is just going to be the exponent. So if you're already familiar with scientific notation, nothing about it's going to be new to you. But if you're unfamiliar with it, before we go further with this and start to see exactly how we would go from, what would that be, 4.5 million to 4.5 times 10 to the sixth, or 0.00453 to the scientific notation we see at the bottom. See if you can identify kind of the process we would use to get there. If you can't get it, no problem. But it might be worthwhile just for your understanding to see if you can kind of figure out the steps we're going to take to convert from the purple numbers we see here on the left of both of those to the scientific notation we have on the right. Because we'll kind of just see the steps on this next slide coming up. So if you want to think through it a little bit more, give yourself some time just by pausing the video. Otherwise, we'll just continue. And like I said, since it's based on a factor of 10, we're essentially just going to be moving the decimal left or right, depending on if it's a big or a small number. And what we're going to be doing is moving that decimal until we get to a point where that number is between 1 and 10. And really, I'll say 9.9 repeating. Just because if it was 10, we would actually just move the decimal over one more and get 0 or get 1. So I'll change that to 9.9 repeating. But if we look at this example here, we can actually see the steps. In this case, it's a really small number, 0.0000514. I think I said the correct number of zeros there. But like I said, we're going to move that decimal till we get to a number between 1 and 9.9 repeating. So in this case, we've got to move that decimal to the right, and we've got to move it 5 spaces. When we do that, we get 5.14 here. So that's our number now. That's the first piece of the scientific notation. Then we always have times 10 to whatever that exponent's going to be. And the way we determine that exponent is just by how many spaces do we move that decimal. In this case, though, we moved it 5, and we have a -5 as the exponent. Just because this is a decimal value, it's really small, we're going to have the negative exponent. So you can see here, numbers larger than 1 have a positive exponent. Smaller numbers, so anything less than 1, is going to have a negative exponent. So that's why we would change, instead of just 5, we have -5. If we had +5 here, that means we would have, what would that be, 2, 3, 514,000. So the positive or the negative exponent is going to have a really big impact. So again, numbers smaller than 1, however many digits we move that decimal is just going to be negative for the exponent, but numbers greater than 1, we'll just have a positive value there for the exponent. And let me clear that again. And with this, let me actually pick 2 of these examples so we can kind of see what I was talking about earlier with the significant figures in scientific notation. But with the first one here, 711.0, if we want to turn this into scientific notation, we need to get that number between 1 and 9.9 repeating. So that means we're going to have 7.11 times 10 to the, and we moved it over 2, 10 to the second. And again, we wouldn't probably even use scientific notation for this because it's still not really a big number. You can see we still have like even more writing now with scientific notation, but just so we can see that practice. But with this one, this 0 was significant, gives us more certainty in that measurement. So when they have significant zeros, they have to be included in that scientific notation. So we'd really have 7.110 times 10 to the second rather than 7.11. So that 0 we have to include because now it's significant. If we look at the example for letter E, and it would be kind of the same thing with G, we've got the 0 at the front. It doesn't represent any value just because we don't even have, if we're thinking about grams again, we just wouldn't even have enough mass to represent that 10th place. But we can also consider it insignificant because if we do scientific notation, we've got to move that decimal to the right too. So we'll have 5.499 times 10. And again, we moved it 2, But in this case, we've got a really small number. So instead of just positive 2, the exponent will be negative 2. But look, we were able to write this value in scientific notation. Still represents the same exact value, still represents the same level of certainty, but we were able to exclude these zeros at the front. So because we were able to do that, that means the zeros here are going to be insignificant. And that's why when we went through this list before giving sig figs, we only had 4 for letter E. So see if you can kind of do that same process for the rest of these. And again, make sure you're considering the number of significant figures. And then if you just want to, as always, pause this one, I'm just going to continue and show the answers just so we can kind of see how we arrive at those. So let me just clear this quick and get the spotlight back. So A and E, we already looked at. B, we're just moving that decimal over 1, but we're moving it over for a small number, so a number less than 1, so that's why it's a -1. And again, we wouldn't use scientific notation for that. That's just extra writing there. Or we typically wouldn't. You could if you wanted to, but generally we would just keep it as 0.293. 90,743. All of those digits are significant, so we'll have all of them in the scientific notation. And we have to move that decimal over 4 to get to that number. So that's why that's the exponent. Same thing with 134.2. We only got to move the decimal over 2 in this case, though. So that's why we've got a smaller exponent than we did for letter C. Letter E we already saw. And then F and G, just that same idea. Seeing how many digits we need to move that decimal. If it's a number less than 1, like with G, that's why we have a negative exponent. A large number like with F, that's why we have a positive 1. But again, with F, 1, 2, 3, 4, 5, we've got 5 zeros that are all significant. And that's why we've got all 5 of these zeros in the scientific notation as well. So just remember the scientific notation actually makes it a little bit easier. If we already had the scientific notation, I should say, makes it a little bit easier to identify the number of sig figs, because any digit included in the scientific notation basically by default is always going to be significant, assuming it's this correct form of scientific notation. If you think about letter F, for instance, we could move this decimal over 2 more to the left and then just increase the exponent by 2. In that case, those extra zeros that we're adding at the front wouldn't matter still. But when we're looking at scientific notation, we always want it between 1 and 9.9. And that's why any digit we include in that scientific notation has to be significant. I should point out, if for letter F, for instance, let's say we didn't have that 0.0, we just had 10,000, then the scientific notation would just be 1 times 10 to the 4th. So really just 10 to the 4th in that case. But because we have that 0.0, that's why we have to include all of those zeros in the scientific notation. Okay, this seems like a lot, but it's really not too complicated. So we'll see a few examples of each of these types of operations. But like I mentioned earlier, depending on if we're doing addition or subtraction, or multiplication or division, we'll have 2 different sets of rules. So with addition and subtraction, round the result to the same number of decimal places as the number with the least number of decimal places. And essentially what that means, if we look at this example here, is if we're adding numbers up, we're subtracting them, we'll still do it the exact same way. So initially, we're still going to treat these operations like we always would. 1.0023 plus 4.383. We're just going to add those up as we normally would. If we plug it into our calculator, 5.3853 is what we're going to get as an answer. But now if we look down here, we can start to see why we're going to have to round our answers a little bit different, and why we're going to do it for the one that's the least precise. So if we look at these 2 values, the first one has 4 digits after the decimal. The second one only has 3. So if we actually kept this as our final answer, And I typically call that the calculator answer because that's just what the calculator doesn't care about sig figs. It's just going to give you the answer for exactly what you plug in. So with the calculator answer, what this sort of indicates, if we were to actually fully report it, just as like we have up here, if we include that 3 at the end, that sort of indicates that with this second measurement, we know that that fourth decimal place would be a 0, which we can't say for certain. Could be a 0, could be a 2, could be whatever it's going to be. So we can only go, our final answer basically can only be as precise as whatever measurement's the least precise. So that's why we just kind of cut it off. And with addition and subtraction, if you do something like this, if you just look to see whatever is the least precise and then just draw a line up and down, that'll just automatically tell you where you need to round to. Just make sure that you have those digits in the same place. So if you think about it, we've got the ones place in the same spot, tenths, hundredths, thousandths, and so on. But if we were to move the 4.383 over 1, then these digits wouldn't be aligned. So that just would screw us up. So we just have to make sure that we have everything matched up in terms of how those hundredths or tenths, whatever it may be, how those places match up. And then when it comes to rounding, this is what the third step is. So it's got a whole big write up there. I took this from I think I took this from the textbook. It might not be though, I forget. But essentially it's just the same way we always round. 5 and above, we round up. 4 and below, we round down. So in this case, since that extra digit, or that next digit, I should say, was a 3, we just keep the 5 as it is. If, let's say, instead of 1.0023 here, let's say we had 1.0027, then we'd wind up with 5.3857. In that case, we would round up the last significant digit that we're going to keep. So in that case, we would have 5.386. But again, it's just the same way we would normally round. So 5 and above goes up, 4 and below we'll just keep as it is. And then with subtraction here, we can see the same thing. 486 minus 421.23. So with this one, we don't really even need to draw the line too much because we've just got a whole number for one of these values. And anytime that's the case, anytime we have a whole number rather than a decimal place, our final answer just has to be a whole number as well. So we'll still go through, get the calculator answer of 64.77, but now our final answer can only go to the ones place. So 64.77, think about it, we're rounding to the ones place. So we're focused on the 4 is where we're gonna round. But since we've got a 7 as the next digit, we're gonna round that up all the way to 65 rather than just keep it as 64. And then we've got a couple examples at the bottom here. So if you want to pause the video and practice with each of these, again, just pause it so you get a little bit extra time. But if we look at it, 2.334 plus 0.31 milliliters, we get, that'd be 2.644. And we'll see it on the next one. What I actually want to point out before we see the answers for these, if you look at both of these examples initially, grams plus grams equals grams. Same thing with B, grams minus grams still equals grams. So with addition and subtraction, we need those units to match up. And one way you can think about that is with height. For instance, if somebody was 5 foot 10 inches, those are 2 different units. So we can't just add them up and get a total of 15. We need to convert either feet to inches to add them or inches to feet in order to get just one value. It's the same thing with this. We can have grams and grams. We can add and subtract those all day. Same thing, milliliters and milliliters for the A at the bottom, or meters for B at the bottom. But with addition and subtraction, we need the same units. Otherwise, we can't add or subtract those values. So in some cases, we may need to convert a particular unit. In some cases, we may just have everything as it is already. But with the unit conversions, we'll see that at the end of the chapter as well. But with A and B for the check your learning examples at the bottom, I'm just going to click to the next slide so we can see those. But with A, 2.334 plus 0.31, that's going to give us 2.6 or 4. So the red number that I just wrote here, this is the calculator answer. But again, we have to round to whatever is the least precise, whatever has the fewest digits after the decimal. And in that case, it's going to be the 0.31. That's going to be the determining factor. So we can only have it 2 decimal places in our final answer. And then since the third decimal, or the third digit rather, is a 4, that means we round down. So we're just going to keep it as 2.64. If we had a 5 here at the end, then we would round it up to 2.65, but that's not the case here. And then with the next one, subtract 55.8752 from 56.533. So when we do that, we actually get, I'll put the decimal there, 0.6578. But again, have to round our final answer for addition and subtraction to match whatever value had the fewest digits after the decimal. That's going to be 3 of them here, 0.533 versus 0.8752. We can only have 3 in our final answer. And in this case, since that 4th digit is greater than a 5, that means we round the third one up. So instead of 0.6578, we're just going to round that to 0.658 meters. And again, you'll see with the answers, they have the same units. It's going to be important that we include those units like we mentioned earlier. And then again, addition and subtraction, those units need to match. So that's why we've got milliliter and milliliter in A, meter and meter in B. And then just to go back for a second to look at the second rule. So again, we have one set of rules for addition and subtraction, where it's just based on whatever value is the least precise. So whatever value had the fewest digits after the decimal, or if it's a whole number, our answer just has to be a whole number. But with number 2, now we've got multiplication and division. Round to the same number of digits as the number with the least number of significant figures. So in this case, it doesn't matter if it's before or after the decimal. We're just going to round our final answer to, or we're going to round it in a way that makes it have the same number of significant figures as whatever value in that calculation had the least. And we'll see a few examples of that. Okay, so if we look at these ones, and again, we have the rule at the top there, but with letter A, multiply 0.6238 centimeters by 6.6 centimeters. If we think about how many sig figs are in those values before we even do the operation itself, we've got 1, 2, 3, 4 in that first value, but we've only got 2 in the second. So because we've only got 2 in that second measurement, we can only have 2 sig figs in our final answer. So if we just go through and see how they set that one up, our calculator answer would be 4.11708. But again, we can only have 2 sig figs. So we check the third one to see how we round that second digit. And in this case, since that third digit's a 1, we'll just round out our final answer to 4.1. But also with this one, note that in multiplication and division, anything we do to the values, we have to do the units as well. So that's why in this case, centimeter times centimeter as the units initially, but then we get centimeter squared for the unit on our answer. So with multiplication and division, we round our final answer to match the number of sig figs in whatever value had the fewest. But we also have to do those operations to our units as well. And that's why with the last or the next one, just looking ahead a little bit, grams per milliliter as our final answer, because we're dividing grams by milliliter in that calculation. But if we think about sig figs again, all 5 of these are going to be significant. All 3 of those are going to be significant. So our final answer just has to match whatever has the fewest, has to match the 3 there. We still go about the calculation the same. So we still get our calculator answer, and we can see we get a small number, but it's got a lot of digits after that decimal. We don't want to include all of those though, because that indicates both of our measurements were extremely precise, which just isn't the case. So we're going to round it to match whatever had the fewest. We're going to round it to match the 3 for the volume there. So we'll just have a final answer of 0.867, excuse me, grams per milliliter. And I should also mention with this, if you had a calculation, so instead of like for the first one there, that could be an area calculation, length times width or whatever of a square, or a rectangle, excuse me. But if we were looking at the volume, if we had a third measurement that we were multiplying by, we would only round at the very end. So do the entire calculation, do both of the multiplication steps, look to see what that calculator answer is, then look to see how we round that significant figure. So don't round if we had like multiple multiplication steps, multiple things that we're dividing, whatever it may be. Don't round each of those steps individually. Just do the calculation as normal, and then that calculator answer at the very end, that's when we'll look to see the sig figs based on whatever had the fewest and round it like that. And again, if you want to practice with the next two, we've got, or the two at the bottom, we've got a couple examples there, multiplying 2.334 centimeters and 0.320 centimeters. And then the same thing, dividing 55.8752 by 56.53, and that's meters and seconds in that case. But to see those answers, I'm just going to click to the next one after I clear this slide. So looking at those two, for the first one, 2.334 times 0.320. So we've got 3 sig figs here, because this 0 is at the end of a decimal, so it's significant. We've got 4 here, but again, we're going to round to the fewest, so we're going to round to 3. That's what we have in our final answer. And then again, we've got to multiply the units as well, so that's why we still have centimeters squared. And then with the second one, we've got 6 significant digits or significant figures here. We've got 4 of them in the time. So we're only going to have 4 in our final answer there. And then, again, got to divide the units. So meter divided by second, meters per second. This is just telling us a speed. Let me actually see. Okay. So we'll go through the accuracy and precision piece actually. So with this one, again, just a few examples. If you want to practice those, go ahead. Again, with multiplication and division, focus on whatever value had the fewest number of sig figs overall. Doesn't matter before or after a decimal, it's just the fewest overall. But then with addition and subtraction, although there's no subtraction here, it's just based on whatever measurement's the least precise. So we have to round to whatever value goes to the least number of digits after the decimal, or if it's a whole number, we'll just have a whole number for our final answer. So as always, just pause the video if you want a little bit more time to work through those, because I'm just going to show the answers in 3, 2, 1. And then with these, we can see the calculator answer at first. So again, with all these calculations, just plug it in as you normally would. But then once we get that calculator answer, that's when we have to think about how are we going to round these. So for A, both of those values, 628 and 342, both have 3 sig figs. So our final answer has to have 3 sig figs. So we're going to be focused on this 4. But because the next digit's a 7, that means we're going to round it up to 215,000. If the next digit had been a 2, we'd have 214,000. And then the next one's kind of a similar case. In this case, again, everything in the scientific notation is significant for the number of piece at least. Don't worry about the times 10 to whatever. Just focus on that first piece. So we've got 2 sig figs in 7.4. We've got 3 sig figs in 5.63. So we've got to focus on whatever has the least. And I actually messed this one up. So this one should actually be whatever one has the least precise. So that would be 4,200,000. So I just looked at the first one, I think. But again, with it, we've only got 2 sig figs here, so we can only have 2 sig figs in our answer. So that means we'll focus on the 1. The next digit's a 6 though, so we'll round that 1 up to a 2 and have 4,200,000 there. C, we're doing division, still fewest sig figs overall, so we've got 3 on top, 5 on the bottom. So we need 3 in our final answer, 2.08. D is multiplication still, so fewest sig figs overall, only got 2 in that second value, 4 in the first, but we've got to match the lower one. So we're going to see an answer of 0.19. We're going to round this value up to 0.19 again, because we've got a 6 in that third digit spot. Actually, for E, I'm going to get rid of that decimal as well. Don't really need that in there. But with E now, we're looking at addition and subtraction. So still get your calculator answer. With this one, though, we're not looking to see which one has the fewest sig figs overall. If we did, we've got 4 sig figs here, 4 sig figs here, 6 sig figs here. But with addition and subtraction, we're just thinking about which one's the least precise. And that's going to be this big number here, 27,340. It's just a whole number, so there's no decimal places, which means our final answer has to match that. And that's why we get 27,440. All right, and then the final one, same idea, a little simpler because we just have 2 numbers, 42.7 plus 0.259. So we've got 1 digit after the decimal in 42.7, 3 in that second value. So we have to match whichever one is the least precise. So we're just going to have 1 digit after the decimal then. So we'll round our calculator answer of 42.959 up to 43.0. But again, for that last one, since we want 1 digit after the decimal, we still want to include that 0.0. We don't want to just say 43. We want to definitely include that 0.0. And then with these ones, we didn't have to worry about the units at all because they're just values. But with addition and subtraction, whatever those units are, we're adding up, would just be the same thing on the final answer. But with the examples A through D, we would need to multiply the units as well in the case of A, B, and D, and we would need to divide the units in the case of C. Okay, and then just a couple more slides to wrap this up for this video. But we've got accuracy and precision. So precision is essentially a measure of how close measurements are to one another, whereas accuracy is how close are those measurements to the accepted value. So if we look at the example here, we've got 3 sort of targets. So you can think of the bullseye in the middle, and the further away we get from that, the further away we are from the accepted value. So in the case of target A, we've got 3 different data points. All of them are extremely close to one another. All of them would be really close to that bullseye. So we would consider this to be accurate and precise. These measurements are close to each other. They're close to what they should be. With target B, we still have those grouped together pretty closely, but now they're getting further away from that bullseye, so they're not going to be accurate. And then with target C, now we don't have them particularly close to one another. They're not really close to the bullseye at all. They're in that furthest ring away. So this would be neither accurate nor precise. And just to give one more example, let's say we had points like this. This would be kind of a case where if we took the average of these 3 x's, they would be pretty close to that bullseye. But none of them individually is accurate, and they're definitely not precise as a collective. And that's why we have, when we're working with data, we have the average to tell us just sort of overall what, as average would suggest, what is the average value there. But standard deviation is also going to be an important piece of that important thing to calculate, because if we were just looking at the X's here versus the three black dots, the averages of each of those would be relatively similar, but the standard deviation for the black dots would be almost zero because they're practically right on top of each other, whereas the standard deviation for the red X's would be extremely high just because they're really far spread out. And with this, depending on if we're doing an experiment or something like that, do you think it would be better to be precise but not accurate, or accurate but not precise? So the red X's that I just got rid of, do you think it'd be better to have that as the kind of the data set that you collected, or something like B? Obviously, this would be the ideal. Everything agrees with each other. Everything agrees with what it's supposed to be. But if that's not the case, do you think it'd be better to have something like this, or something where the points are scattered, but they do average out to what they're supposed to be? And depending on what you're doing, there may potentially be a reason for one or the other. But in general, I would say this is better. And I'll put the X's again. I would say being precise but not accurate. So I would say the black dots in this case would be better, because what this tells us is there's one issue with whatever this is. Whatever this experiment is, if we get these three black dots here in picture B, that tells us what we're doing is repeatable, but it tells us that there's some error. It may be something that we do consistently wrong. There may be some measurement device or piece of instrumentation, equipment, whatever it is, that's just not calibrated properly. The concentration of a particular chemical may be off, but whatever we're doing here, if we get precision but not accuracy, is repeatable, and we could go back and try to figure out what that error is. And since it's precise, it's likely to just be a single error. We could then correct that and not only get precision, we could get accuracy. But with the case of the red X's, if our average is accurate, but we're not precise, what that indicates is what we're doing is not repeatable. We have some sort of error that's changing each time, basically. So we're either screwing up a bunch of stuff and just happen to get lucky that the average was on there, or we're screwing up different things each time. And again, in that case, that's just not what we want to see, just because science should be repeatable. And of course, not accurate, not precise. Worst case scenario, but in my mind, there's really no difference between not accurate and not precise and these red dots here, or red X's, because even though these average out to the correct value, it's just by like chance, essentially. So in my mind, precision is better than accuracy, just because that shows us what we're doing is consistent, whereas just being accurate overall in terms of the average doesn't mean too much in some cases. But again, obviously, target A would be the ideal that we strive for. And then with this type of situation, that would be what we would call a systemic issue, something that's consistently present. So if we could address that issue, we could then wind up grouping all of these data points right where they should be. And with these, take a moment to see if you can figure out, again, kind of similar to that target, figure out what are accurate and precise. So in this case, this is a cough medicine delivery system, just a dispenser that's going to dispense 10 ounces, which is equal to 296 milliliters. So essentially what somebody would do is have 3 of these dispensers and then record the volume that is dispensed from each of them. But in science in general, we want to do stuff as much as possible just to get as large of a data set as we can. So if we just did it once for each of these dispensers, we'd be able to see that this one is not accurate. Both of these, though, we'd see this one seems very accurate. This one, not too far off, so still pretty accurate. But by doing multiple tests of each, we can then get an idea of the precision as well. Because if we look at dispenser 1, it's supposed to be 296 milliliters. These are all about 284, 283. So they're all pretty far off, but they're all the same thing. So this would be, again, an example of precision, but not accuracy. Dispenser 2, again, we look at just 283, we'd see, okay, that's pretty close. If we saw just 294, kind of same thing, because it's pretty close, just in the opposite direction. But now we can see with the entirety of this data set for dispenser 2, that it's not precise at all. It's not, I don't want to say not at all, because again, these values aren't too far different from one another. But when we compare them to the other three, or the other two, excuse me, which are all basically the same thing, you can see that the range in this case goes from 283.3 up to 284.1 that we have a couple times. So there's a 0.8 milliliter difference there. In this case, it's pretty much spot on the entire time. It's a 0.2 milliliter difference, 259.9 to 296.1. Whereas this one, 293.9 all the way up to 298.3. So that's a 4.4 milliliter difference. So in comparison, this one is not precise at all. We could still potentially consider it accurate with like quotes around it, because the average would likely be pretty close to 296. I don't know exactly what it is. But again, without precision, that accuracy isn't really important, because each time we do this, we're going to get something completely different. And especially if we're thinking about this is cough medicine, which likely doesn't matter too much in terms of these small differences. But we have pipettes in research sometimes that work very similarly, where they're supposed to dispense a very precise amount of liquid. Even just something as small as this, so a couple of milliliters out of almost 300, might not seem like a big deal, but that could have a huge impact on certain types of research. And depending on the medicine even, it could as well. So again, cough medicine, probably not that big of a deal to be off by like 1% basically. But in some cases that could have big impacts. And then number 3 is going to be accurate and precise, because all of those values are within 0.1 of what they're supposed to be. And with this one, I said better accuracy, but again, without precision, that accuracy doesn't really mean anything, because it's just kind of bouncing around. We don't know what it's going to be at any point. At least with this dispenser here for the first one, it is very precise. So we can be certain whenever we use this one that it's going to be like 284. Whereas this one, we might get 293, we might get 298. So it's going to be a pretty big range by comparison. And then with the last piece is going to be dimensional analysis, but I'll save that for another video. If you want to get a jump start on it though, Tyler DeWitt uses a very similar sort of process that I'll demonstrate, where we're just basically canceling out units to get to the unit that we want. So if you wanted to, you could search or go to the notes on Canvas and find these videos, or just search these in YouTube. If you just do Tyler DeWitt dimensional analysis, they should come up.